Section: Introduction. In this section, we discuss the current state of large language models, LLMs, and their journey toward achieving human-like artificial general intelligence, AGI. While LLMs have made impressive strides, they still lack the self-regulation and understanding that characterize human intelligence. During their pre-training, LLMs absorb knowledge from extensive text data, and in the supervised fine-tuning, SFT, phase, they learn to follow instructions through question-answer pairs. However, both phases treat LLMs as passive learners, overlooking their potential for active learning. Aligning a base model from the ground up requires a lot of high-quality data across different tasks, which is a labor-intensive and time-consuming process. Unlike humans, who can automatically answer questions after gaining knowledge without needing explicit training, LLMs need a new approach. We believe that exploring active, automatic, and continuous alignment, similar to human learning, is essential for LLMs to progress toward AGI. Several methods have been developed to align base models in low-resource settings, aiming to reduce dependence on human guidance. For example, techniques like Self-Instruct and Dromedary use self-generated data for improvement, while Magpie prompts stronger models to create instruction output pairs. Although these methods show some proactive behavior, they still fall short of the continuous alignment seen in human learning. Research in education highlights the importance of metacognitive self-assessment in ongoing alignment, as it helps learners reflect on their knowledge and manage their cognitive resources. Inspired by this, we introduce a new paradigm for LLMs called iSheep, which enables them to align themselves proactively and continuously from scratch, even with minimal external input. iSheep starts with initial data and utilizes the LLM's capabilities to generate more instruction output pairs. We then incorporate self-assessment, allowing the model to evaluate its learning and filter out incorrect information while retaining accurate knowledge. This iterative process enables the model to align itself continuously based on its internal understanding. Our main contributions are as follows. 1. We propose iSheep as a human-like learning framework for LLMs, facilitating active and continuous self-alignment using only internal knowledge. 2. We integrate metacognitive self-assessment into the alignment process, enabling the model to manage its learning. We also explore how different levels of metacognitive abilities affect the efficiency of iSheep. 3. We find a strong connection between self-enhancement potential, metacognitive self-assessment levels, and model size, and we conduct experiments to evaluate iSheep's performance across various model sizes and metacognitive levels. Next, we address related work in automatic data selection, emphasizing that the quality of datasets is more important than quantity during instruction fine-tuning. Some studies focus on selecting high-quality subsets from larger datasets to enhance model performance and training efficiency. We introduce an instruction following difficulty metric to select the best data for fine-tuning, but our iSheep framework does not rely on specific metrics or external assistance. We also discuss the generation of synthetic data, which involves using LLMs to create new data that mimics real-world scenarios, reducing the need for manual labeling. Some methods improve models using self-generated data, while others use powerful closed models to enhance open-source models. Our iSheep framework shifts from a static improvement approach to a dynamic, continuous self-enhancement process. Section Summary. In this section, we introduce iSheep, a novel paradigm for large language models, LLMs, that enables them to proactively and continuously self-align from scratch using their internal knowledge, inspired by human learning processes. We emphasize the integration of metacognitive self-assessment to enhance the model's ability to monitor and improve its learning, thereby addressing the limitations of current alignment methods that rely heavily on external supervision. Section: Iterative Enhancement for LLMs. In this section, we discuss iterative enhancement for language models. We explore various methods that utilize strong models or external tools. For instance, Iteralign uses powerful models like GPT-4 and Claude 2 to identify and fix errors in responses from basic language models, thereby improving their safety. These iterative enhancement techniques often rely on robust models to ensure continuous optimization and prevent model degradation. Some approaches also investigate iterative enhancement during the reinforcement learning from human feedback (RLHF) phase to better align models with human preferences. However, we focus on the continuous self-alignment of the base model from the ground up. Next, we introduce self-driven data synthesis. Our method, Self-Instruct, uses a readily available large language model to create synthetic data. We start with a small set of 175 prompts, referred to as the seed task pool, and leverage the model's capabilities to generate a wider variety of prompts and responses. We will explain the self-driven data synthesis process from two angles: instruction generation and response generation. To maintain consistency in data creation, we adopt a standardized instruction format from Alpaca, which allows us to generate instructions along with their potential inputs. For instruction generation, we take prompts from the seed dataset and a metaprompt from Alpaca. The model generates a new set of prompts through in-context learning, where each new prompt is derived from a subset of the seed dataset. For response generation, once we have our set of prompts, we use the model to create corresponding responses without any prior examples. To ensure the quality of our self-enhancement data, we implement a two-stage process: self-assessment and data filtering. In the self-assessment phase, we pair the generated prompts and responses to create instruction output pairs. Given the limitations of models, assessing the quality of these synthetic pairs is crucial. Since manual assessment is often impractical, we introduce an automated evaluation method where the model independently assesses each response's quality and adherence to instructions, scoring them based on predefined criteria. In the data filtering phase, we remove entries that do not meet our quality standards. This ensures that only high-quality data remains, enhancing the reliability and usefulness of our dataset. Initially, we apply heuristic rule-based filtering during data generation, and afterward, we filter the instruction output pairs based on the assessment scores, using a threshold to retain only the best entries. Finally, we describe our iterative self-enhancement algorithm, which aims to progressively improve a language model by generating and using high-quality synthetic datasets. Starting with an initial model and a small seed task set, the algorithm iterates through a set number of steps and a filtering threshold. In each iteration, we generate a new set of prompts and corresponding responses, creating a raw dataset. This dataset undergoes self-assessment to evaluate response quality, followed by filtering to keep only high-quality data. We then train the model on this refined dataset, enhancing its performance through supervised fine-tuning. This process continues until we reach the final step, resulting in a stronger language model and a refined synthetic dataset. Section Summary. In this section, we describe our iterative enhancement approach for language models, which utilizes strong models to generate high-quality synthetic datasets through a process of prompt and response generation, followed by automated self-assessment and data filtering to ensure quality. This iterative process allows us to incrementally improve the model's performance by training it on refined datasets, ultimately resulting in a more robust language model. Section: Chat Evaluation. In this section, we evaluate how well-aligned models follow instructions and the quality of their responses using three chat benchmarks: Alpaca Eval, MT Bench, and IF Eval. These benchmarks are chosen for their thoroughness, detailed scoring, and reproducibility. Both Alpaca Eval and MT Bench use GPT as the evaluator, while IF Eval offers 4 types of accuracy scores: strict accuracy at the prompt and instance levels, and loose accuracy at the same levels. We also utilize the Open Compass evaluation platform, which provides a wide range of benchmarks, including BoolQ, PIQA, SIQA, Hella Swag, Wino Grande, ArcC, OpenBook QA Fact, Common Sense QA, and MMLU. Additionally, it features code generation benchmarks like Human Eval and MBPP, a word knowledge benchmark called Trivia QA, and a reading comprehension benchmark known as Squad 2.0. For our experiments, we focus on the QWEN 1.5 and Llama 3 models to test the effectiveness and generalization of iSheep. We examine how different model sizes affect iSheep by testing various sizes of the QWEN 1.5 model, ranging from 1.8 billion to 72 billion parameters. Each training dataset is generated by the model from the previous iteration, and we provide case studies and quality analyses in the appendices. We use Llama Factory for fine-tuning with specific parameters outlined in another appendix. Each iteration takes about 4 hours on a specific NVIDIA setup. During self-assessment, we propose 3 evaluation methods: a simple standard prompt, a combined standard prompt, and an in-context learning prompt. The details of these prompts are available in an appendix. In the filtering phase, we implement 6 different settings, including various prompt-based filtering methods and 2 that do not rely on external tools. For instance, we use the model's own perplexity value to filter out low-quality data, specifically removing data points with a perplexity greater than 50. We also apply density filtering by clustering data and sampling from each cluster to maintain diversity, setting the number of clusters to 3,000. The combined filtering method clusters the data first and then selects samples with lower perplexity values. For our baseline, we compare our approach, iSheep, against the base model, Self-Instruct, and Dromedary. Self-Instruct is a one-time alignment method where models are trained on their generated data without self-assessment, while Dromedary also follows a one-time alignment process based on specific principles. In our iterative settings, we explore how iSheep affects efficiency by using data from the last iteration to train the base model, the last iteration model, or all previous iterations. We also generate additional data points for comparison to assess the impact of data size. In the first iteration, all settings are the same, with the base model generating and filtering 10,000 data points for fine-tuning. For ablation settings, we adjust key variables like the self-assessment threshold, data size during generation, and iteration steps to see how they influence iSheep. We also conduct experiments with varying levels of self-assessment, including no assessment, assessing only response quality, only instruction following, and both aspects together. Section Summary. In this section, we evaluate the instruction following ability and response quality of aligned models using various benchmarks and the Open Compass platform, while conducting experiments on different model sizes to analyze the effectiveness of our iSheep framework. We also explore self-assessment and filtering methods to enhance data quality, and investigate iterative and ablation settings to understand their impact on model performance. Section: Main Results. In this section, we present our main results. The table illustrates the experimental performance of different model sizes over various iteration steps. We discovered several key findings. 1. iSheep shows effectiveness across various model sizes, especially with the 72B model. It achieves a maximum relative improvement of 78.2% in the Alpaca eval, 24.0% in the MT bench, and an absolute increase of 8.88% in strict accuracy on the IF eval prompt level over subsequent iterations of the QWEN 1.572B model. Additionally, iSheep outperforms the base model in standard benchmark generation tasks, with an average improvement of 24.77% in code generation, 12.04% in trivial QA, and 20.29% in squad. However, we noticed a significant drop in scores for the second round of dialogues after the 4th iteration, likely due to our generated data being limited to single-round dialogues, which may negatively impact the second round. More details are available in Appendix D2. The potential for improvement varies by model size. The smaller models, 1.8B, 4B, 7B, and 14B, show improvements over 2 iterations, while the 32B and 72B models improve over 3 and 5 iterations, respectively, according to the IF eval benchmark. In the iterative setting results, we present the chat benchmark performance for the QWEN 1.572B model across different iteration settings. With more results in Appendix C, our findings include: 1. Training the base model with data from the last iteration is effective for iterative self-enhancement. In the 1_base setting, using last iteration data at the third iteration yields the highest performance on the chat benchmark, indicating potential for further enhancement. Thus, we selected the 1_base setting for all subsequent experiments. 2. The size of the data is not the main factor affecting iterative improvement. Training the base model with last iteration data at the third iteration outperforms using a combination of all previous iteration data. In the threshold ablation section, we observe that as the threshold increases, the performance of iSheep at the third iteration improves. We selected a threshold of 8 to allow for further iterative improvement, given the significant performance gains from the second to the third iteration. However, thresholds of 6, 7, 8, and 9 are all viable options. In the data size ablation analysis, we see stable improvements in the first 3 iterations across various data sizes: 10K, 20K, 30K, 40K, 50K, demonstrating the robustness of the iSheep framework. The model performs well at the third iteration with a data size of 10K, showing significant improvements from the first iterations. Considering these factors and resource efficiency, we chose 10K as our final data size. For the self-assessment robustness analysis, we present the performance of different self-assessment degrees in the first 3 iterations, with more benchmark results in Appendix C. Our findings indicate: 1. Using explicit self-assessment prompts is more effective than relying on simple model internal states, as the highest accuracies are achieved with explicit prompts. 2. The iSheep framework is robust to different prompts. Despite variations in criteria between simple and combined standard prompts, their performance remains similar. Even without a designed prompt, using a few examples for in-context learning can yield comparable results. In the self-assessment level analysis, we explore the efficiency of iSheep across various self-assessment levels. Our key findings include: 1. Higher levels of self-assessment lead to greater improvements in the efficiency and potential of the iSheep framework. Evaluating both quality and instruction following achieves the best performance at the third iteration compared to other settings. 2. Assessing the degree of instruction adherence in data pairs is more effective than solely evaluating output quality. The instruction adherence group outperformed the quality group at the second iteration on the IF eval benchmark. Lastly, we conducted experiments on the Llama 370B model to confirm the effectiveness of the iSheep framework for other models. The results show that Llama 3 is also enhanced iteratively through the iSheep framework, with significant improvements between the second and third iterations indicating its potential for further enhancement.